PhD from Princeton in 1989, did postdoc at Cornell. Point is, I know Brad's work, many people know from on the so-called flux phases, strongly correlated. He's a condensed matter theorist, worked on strongly correlated systems. Some people may remember something called flux phases from the early days of high temperatures superconductivity. Okay, but he also took keen interest in things like climate change and so on, so his long-term passion. He will give a colloquium tomorrow about this. So long story short about this particular colloquium, this particular seminar. So about a year ago, January last year, I was giving a colloquium at University of Colorado Boulder. And on that occasion, I just browsed their video recordings of their colloquia. And I stumbled upon, Brad Marston's talk on this subject about topological waves on the Earth, which is, of course, a very interesting subject. Closely related to quantum Hall effect, etc. So I think it would be great to bring him here to give talk about this subject, because many people worked on this same story in quantum context, but he will tell us about same story in geophysical context, which is quite interesting. Brad is elected president of American Physical Society for this year, 2026. So I thought that he will be coming to DC on this APS business, and I basically wanted to use this opportunity for him to come here. And give this talk about topological waves today and general colloquium tomorrow. Okay, please. So put this microphone. This is for people on Zoom, right? Yes. Yeah, this microphone is not for the audience, it's for people on Zoom.
Very good.
And this is a pointer. Did you instruct how to use it?
Yeah, thank you. Yeah, thank you for that kind introduction. Yeah, it's a pleasure to be here at JQI. I haven't visited before. Let me see where Yeah, I think that'll be good. Yeah, so this is the Quantum Institute. I'm not going to be telling you too much about quantum physics today, but I'll begin with a little bit of quantum physics, because I want to tell you about waves of topological origin in the fluid Earth system and beyond. It's some work that we've been doing since 2017 with a large number of collaborators, some of whom are shown here. It started with my two French collaborators at ENS de Lyon. And I'll be also highlighting some work with Zoe Zhu, who's now a new professor at Boston College. There's a number of names that aren't on this list, but these are the main people that will be highlighted today. Okay, let's see. I advance this. Right. Okay, great. All right, so here's the outline of this talk. I want to review very briefly topology and quantum matter, and then talk about classical lattice systems that support the kinds of waves that I'll be talking about today. Then we'll turn to the continuous fluid Earth system, and I'll note the existence of broken discrete symmetries, which are going to be important. And then the mathematical heart of the talk will be the shallow water equations for fluid motion. And we'll analyze their topological character. And then we'll look at some applications to the climate system, the El Niño Southern Oscillation, and some other oscillations in the Earth climate system, and look at actual observations of the atmosphere and in the stratosphere. And we'll also look at some other waves of topological origin. And this seems to have gone. There we go. Okay, it's going in and out. All right, so topology has been playing a role in physics for quite a few decades. Most of that has been concentrated in real space structures such as vortices or hedgehogs or various topological defects that are present in condensed matter or fluid systems. But the type of topology I want to talk about is really more at home in wave vector space. And it really entered physics through the quantum Hall effect, And through the integer quantum Hall effect, the surprising discovery that the Hall resistivity didn't have a linear dependence on the magnetic field applied to, say, a Hall device here, a little bit of semiconductor in a magnetic field with leads attached, but instead, of course, showed these steps in the resistivity that von Klitzing discovered. And now this is actually an international standard for resistance because these steps are so precisely quantized. Now, a kind of mechanistic view of what's going on here is that if we think about the cyclotron orbits of electrons in a magnetic field, then they're going to be going around in circles, but at the edge of the system, then those circles can't complete their orbit. Instead, you have this kind of skipping motion going along the edge in a unidirectional way. And what that means is that if there's some disorder, some impurities in this early Hall device, you can see that it's really quite messy. Then instead of the electrons scattering in all directions off of this impurity, then they're dragged forward in this unidirectional way. So that gives a kind of a sense for topological protection, although the topology is not yet evident here, this idea that there's some sort of protection against scattering. But the real explanation for the precise quantization of the plateaus, the most, at least in its mature version, came through the work of David Thallis and his collaborators, where they applied a linear response theory, the Kubo formula, to calculate the Hall conductivity in one of these bars. And you can see the units of E squared over H here, times this integral. And they didn't realize it at the time, but they realized that this integral was an integer. They didn't realize that mathematicians had already discovered this, and it's something called the Chern number. So it's a measure of the non-trivial topology of the bands in this quantum system. Because of this, the fact that this integral is an integer, then the Hall conductivity is quantized in these units of E squared over H. So I'm not going to go through the derivation of this in any detail because we're going to be looking at something very similar in a classical fluid system a little bit later. So what's topology? Topology is basically the qualitative shape of things. So there's the famous example of a coffee mug that, if it was made out Play-Doh, could be continuously deformed into a donut without tearing the Play-Doh. And although this is in real space, topology can occur or can be characterized in more abstract spaces. Here's another example in a real space, which is the Mobius strip. And as you know, in the Mobius strip, you have say a piece of paper, and if you have a half twist in it and you glue it together, then this is a non-orientable surface. If we wanted to make it an orientable surface where the inside, there's a definite inside and a definite outside, we have to cut this paper, untwist it, and tape it back together again. So we'd have to do something violent, not a continuous deformation. Something a little bit closer to what I'll be talking about is the hedgehog theorem, or the hairy ball theorem, which says that if you have a sphere and you try to cover it with a vector field and comb that vector field flat on the surface of this sphere, then there will always be a defect. There'll be basically a cowlick, or someplace where the vector field doesn't lie flat. And that's in contrast with the situation on a torus, where you could comb the hair flat everywhere. And so here's a actual hedgehog, which don't live in North America. But when I was first starting to think about these ideas, I was on sabbatical in near Lyon, France, and we had one of these creatures in our backyard that I inadvertently uncovered in the fall when I was raking leaves, and had to figure out how to bury it back, let it hibernate. And so I like to think that it was sending me some sort of signal to pay attention to topology, which I wasn't yet ready to receive. Now, in the Feynman lectures on physics, Feynman, in the chapter on fluid dynamics, says the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today, we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence one sees between rotating cylinders, rotating Couette flow. Today, we could not see whether Schrodinger's equation contains frogs, musical composers, or morality, or whether it does not. And so I'd like to argue that the tools of topology give us a small sense of motion in this direction towards qualitative understanding of equations, and because it will turn out that it can turn some complicated problems into simpler ones. So before we leave the quantum world, I'll just remind you about topological insulators, where in the absence of an applied magnetic field, still there's some interesting physics going on. And roughly speaking, you can have a situation where spin-up electrons are traveling one direction on the edge of this material, and spin-down electrons are traveling in the opposite direction. And the reason I bring this up is that the band structure can be observed. This is a predicted dispersion relation for the energy versus wave number, and we can see these two counterpropagating modes for the different spins on one side, one edge of this material. And this has been seen in angle resolved photoemission spectroscopy, where we see these two linearly dispersive modes. And this is possible here in these materials because the energy scale is a lot higher than in the quantum Hall effect. And so angle resolved photoemission spectroscopy can see this. But what I'm going to show you shortly is that actually atmospheric scientists saw this spectrum before quantum scientists did. Now, the key aspect of this is not really the quantum aspect, but the fact that there's a wave equation, there's a wave amplitude. So that means that in some classical systems, one can expect to find waves of topological origin. And here's just a small set of the many examples now. This one we're going to look at in a little bit more detail. This is a collection of gyroscopes that are suspended from the ceiling and are coupled to each other with little magnets so that they can oscillate and the disturbance can propagate through them. But there's also optical systems, acoustic systems, various other classical wave systems, all on lattices, though. So all on lattices, just like the quantum Hall effect and the topological insulators. So let's look at this system. This comes from the lab of William Irvine at the University of Chicago. All of the these little toy gyroscopes are all spinning in the same direction. And so when some excitation is created by jiggling one of them, then we see a wave that's going to propagate around the edge of this system. If the gyroscopes were not spinning, the energy would propagate into the interior. But because they're all spinning in this one way, as we'll see, then there is a edge mode, and the energy is prevented from penetrating into what we'll call the bulk, the region deep inside the system. And the color is just highlighting where the maximum amplitude is in this experiment. So we became interested in asking the question of whether the continuous fluid Earth system might support these waves, because the Coriolis force, which acts at right angles to the velocity in a rotating system, functions much like a magnetic field. Mathematically, it looks very similar to applied magnetic fields. So perhaps some of the quantum Hall type physics could appear in a fluid system. And just to highlight this a little bit further, let me remark that there's the CPT theorem, which says that physics is invariant under the combined operation of charge conjugation, parity, and time reversal. So I'm going to be talking about neutral fluids right now. So we'll just consider parity and time reversal. And let's consider a rotating planet. If we were to look at this planet in a mirror, the sense of rotation would be in the opposite direction in the mirror. So that's the parity operation. But then if we were to reverse the direction of time, take a movie and then play it backwards, that would restore the sense of the rotation. So the combination of parity and time reversal leaves the system invariant. And algebraically, we can see that by looking at the acceleration in the non-inertial rotating frame. It's not given just by F over m, but has these corrections due to the Coriolis force and the centrifugal force, these fictitious forces. And if we see the velocity is one derivative of the position with respect to time, the acceleration has two derivatives with respect to time. And therefore, under time reversal, under t goes to minus t, the form of this equation would change unless we also reversed omega. So that's just the algebraic encapsulation of this PT theorem. Now, in the fluid Earth, most of the motion is in the horizontal direction. And that means that what we're most interested in this Coriolis force is the vertical component, the local vertical component of the rotation of the Earth. So if we're here in College Park, when we look straight upwards, we want to look at the component of the Earth's angular rotation rate in this vertical direction. So we take the dot product of these two things. And what we will find, I guess we have this equation down here, is that we get this angular rate of rotation times the cosine of the colatitude. So this is the quantity that's equal to pi over 2. This is the usual coordinates of physics. So it vanishes at the equator, and this Coriolis parameter f, which has a factor of 2 in it because of this factor of 2 here, changes sign across the equator. It's called f because it's the same thing that appears in the formula for the precession of a Foucault pendulum that probably all of you have seen in a science museum. So the equator is a special place. It is the interface between, as we'll see, two topological insulators that break time reversal symmetry in an opposite sense. And it's in this sort of situation where we might expect to find waves localized along the equator that have a topological origin. So when we were first thinking about these ideas, I talked to a number of experts in topological physics, and there were some objections raised. Okay. The objections have been dismissed. Okay. One is, well, maybe this system is too simple. The fluids are pretty simple. We'll see that that's actually, that can be dispensed with right away. More profound objection is there's no lattice. We have a continuous system. And so for those sort of experts in the audience know that when we're computing a Chern number, we want to integrate over a Berry curvature over a compact Brillouin zone. If there's not a Brillouin zone, then the result can be indefinite. So maybe the lattice is important. And finally, we could ask the question of whether this bulk interface correspondence holds. That is, understanding the topology of the waves far away from the equator or the interface tells us something about their behavior at the interface. That's the key conceptual idea that is present in all of this, including going back to the work of Thales, where that integral was calculated over all space, but tells us something about the behavior of the motion of the electrons around the edge of the system. So if we look at the fluid Earth system here in an infrared channel that's sensitive to water vapor, we can see that there is two distinct types of regions. The low latitudes near the equator and the high latitudes. At the high latitudes, where the Coriolis parameter is very strong, then we get this nice wave-like motion. And this is basically the succession of storms that pass through at the latitudes such as in Maryland. In low latitudes, we see actually that the motion is in the opposite direction. The trade winds are carrying things from the east to the west. And this pulsing that you're seeing is the buildup of thunderstorms during the daytime and then going back in the nighttime, decaying in the nighttime. So I had been paying most attention to this simpler region away from the equator, which was more wave-like dominated, and thought that this equatorial region was too complicated for the kind of statistical approaches that I was trying to develop. But as we'll see, that was throwing out the baby with the bathwater, and it's actually this equatorial region that we want to focus on. So just to emphasize this, a number of years ago, we were searching for a condensed matter experimentalist. I was on the search committee, and when they came into my office, I would hand them this book in geophysical fluid dynamics, and they would wonder why I'm handing it to them. But it was I had a page mark in there, and they opened it up to that page mark, and they saw this diagram, which is the dispersion relation of a edge mode, a Kelvin wave. And of course, as soon as they saw this, since they'd all been going to seminars after seminars on topological materials, they knew right away what was going on. And if I had been paying closer attention to things, I would have realized these connections much earlier. So in fact, it was Lord Kelvin who first wrote down an edge mode that has a topological origin, as we'll see in just a moment. But let's do a little experiment, or we'll let this Japanese lab do a little experiment. This is looking down on a wave tank, and it has two fluids, a lighter fluid over a denser fluid. And there's a buoyancy force. If we push down the interface between these fluids, it will want to respond, pushing the lighter fluid back up. And this is an optically active fluid, so it makes it easy to visualize through polarizers the vertical motion. If I set this into motion, then this wave tank, you can see there's a wave generator that's just emitting waves into all the different, into the whole space. But if I now set this wave tank into rotation, and the camera is rotating with the wave tank, it's in this non-inertial frame, then everything else is the same, but now the wave propagates around the edge. This is our coastal Kelvin wave, which is another interfacial wave, and you can see it has this unidirectional sense. So very much like in the integer quantum Hall effect. And this is Kelvin's paper from 1879 on gravitational oscillation of rotating water, William Thomson. And it's eminently readable. It's very short. It's only like 2.5 pages long. And here's his exponentially localized wave function trapped near the boundary of the system, near the edge. He was thinking about the English Channel and waves traveling along the French coast. And it has a linear dispersion relation. So it's the first wave of topological origin, although he wasn't aware of the connection to topology. He simply solved directly the wave equation. So let's look at a simulation for our rotating planet. What we're going to do is, again, have a denser fluid underneath a lighter fluid. So we call this stably stratified. And we're going to create a disturbance, so dropping in a rock effectively, causing waves to propagate outward. And when we do this on a sphere, though, the waves propagate outward and they go to the antipode and pass through each other, and then they come back, and they'll just go back and forth this way. Here's a view on a cylindrical projection, the waves passing through. this is not rotating. If I turn on rotation, there's now two restoring forces. There's the force of buoyancy and this in the vertical direction, and there's the Coriolis force in the horizontal direction. Now, for the same initial condition, we have this tightly localized wave, this equatorial Kelvin wave traveling along this boundary between the two hemispheres. There's actually a second wave called the Yanai wave, which is antisymmetric with respect to north-south symmetry. And you can see that unlike the Kelvin wave, it is highly dispersive. Its group and phase velocities are different. So it has this kind of phasing character that is evident. So you can generate these waves with this app that I put on the Mac App Store for free called GCM, which I use for some of my research when I'm interested in waves on spheres. Now, the Earth actually gave us a nice kind of example of one of these waves not too long ago with this massive explosion, eruption in the Pacific Ocean, the Honga Tonga eruption, that sent a wave out, and you can see this pressure wave passing out at the speed of sound, and it went around the Earth multiple times. It's very similar to what we saw in the simulation, except that this is a longitudinal wave. It's a pressure wave, a compressional wave, so it wasn't affected by the Coriolis force, so it expanded symmetrically. Well, are these waves important? Yes, the equatorial Kelvin wave has long been recognized as being an important component or essential component of something called the El Niño, the oscillation that occurs along the equator. And this is what we're seeing is a visualization from a NASA satellite measuring the sea surface height using radar. And I'll set this into motion. And you can see this unidirectional wave moving across the equator of the Pacific. The amplitude of the motion is about plus or minus 20 centimeters. And positive height is colored red here because it corresponds to warmer water. When water warms, it expands, and so it raises the height. And when there's this pool of warm water off of the coast of South America, it has, we're in the so-called El Nino phase, which has worldwide effects on climate. Currently, we are in the La Nina phase, and which may have something to do with the differences that we're experiencing here in the winter compared to the last 3 years when we were in the El Nino phase. This is a three-dimensional view of a equatorial Kelvin wave, not from satellites, but from floating instrumented buoys that are floating around in the oceans. There's thousands of them. One of the great breakthroughs in ocean science has been to deploy these Argo arrays to measure the three-dimensional profile of the ocean. We have a much better understanding of the ocean from this. So now let's turn to the mathematical heart of the talk with the shallow water equations. So again, I want to think about a denser fluid underneath a lighter fluid, or this upper part could just be a vacuum if you like. And the equations of motion are these equations, these partial differential equations, in the limit in which the wavelength here is long compared to the depth. So that's the shallow water part of these equations. And these equations are basically expressions of conservation laws. This first equation is the conservation of mass. It says that if there is a divergence in the horizontal direction of, say, this bulge of fluid going outward, then the height must drop because the fluid is conserved. So, so positive divergence here means that dt, the time derivative of h, is negative. And then the second equation is basically the conservation of momentum, or F equals ma. It says that the time derivative of the velocity is due to the two forces, the buoyancy force, there's the acceleration of gravity, and the gradient of the height, and then the Coriolis force that we recognize with this cross product. The only complexity here is that there is this additional term because we're talking about the advective derivative. We're thinking about the acceleration on a parcel of fluid, and so we have to follow that parcel of fluid. We can imagine putting some dye into the system, and as that, we're not just at a fixed point in space, but we have to follow that parcel of fluid as it moves along. So that nonlinearity is the source of much of the richness in our fluid equations, for example, turbulence. There's also nonlinearity here, but we're going to linearize these equations because we're going to look at small amplitude oscillations about some mean height. And if we linearize it, we can drop this term here, this u squared term, and we can replace this little h with big H. Now the equations are linear, and if we put them in a periodic box, we can find the normal modes by just using plane waves, having waves of definite wave number. And that will replace the spatial derivatives by the wave numbers kx and ky. And so we just need to diagonalize this 3x3 matrix to find the spectrum or the dispersion relation of these waves. So that's easily done. And the dispersion relation looks like this. There's a completely flat band, and then a positive and negative frequency band that are separated from this zero frequency, zero mode by the Coriolis parameter f. So f is a frequency. So this is beginning to look like some things that we see in, say, condensed matter systems, where we know that there are topological transitions. This flat band is what is known as geostrophic balance. That's simply the idea that around high pressure regions in the northern hemisphere, you can have circular motion balancing the Coriolis force against the pressure gradient. So they move in a clockwise direction. In the southern hemisphere, they move in a counterclockwise direction. And there's no frequency, no oscillation associated with it. It's just a continuous motion. These gravity waves are those ripples going out that we saw when the rock was dropped in the pond, except that they've become gapped because of the Coriolis parameter. And if we look at the wave amplitudes, we see our first hint that there's some non-trivial topology because the phase of these waves oscillates rapidly as we go around the origin in wave vector space. So there's a singularity in wave vector space, and that's the topological signature that we're going to zero in on now. So let's consider the behavior of those bulk waves, the ones where we are far away from the equator, where we impose periodic boundary conditions as a function of the Coriolis parameter, where we go from the South Pole, where it has its most negative value, to the North Pole, its most positive value. And so here's our dispersion when we're far away from the equator. And if we plot the complex amplitude, if we use an arrow to indicate the argument of the wave function, we'll find that there is an anti-vortex around the origin. And I'm going to associate that. That's for the positive frequency band. And so I've colored it blue or negative. Think about that as an anti-vortex. So it has a winding number -1. As we go around the origin here, the arrows rotate in the opposite sense as our direction of rotation. And this can be done in a gauge invariant way by multiplying the y component of the velocity by the complex conjugate of the height field. In the northern hemisphere, by contrast, the positive frequency band has a vortex. So the phase of the complex number of the amplitude rotates around in the same sense as we're going around the origin. And so I've colored it orange up there to indicate that it's a winding number +1 or positive. And therefore, there is a topological transition that must occur as we go across the equator. A band inversion happens. This negative frequency, positive winding number band becomes a positive frequency, positive winding number band. And right at the equator, where F is 0, then the bands touch and they lose any definite topological character. That's where the transition occurs. And it's at this point that we have these two edge modes, the Yanai wave and the Kelvin wave. So that, in a nutshell, is the topological argument that I want to continue exploring. Oh, so the winding number changes by 2, from -1 to +1, and equivalently, the Chern number also changes by 2, the difference in the Chern number between the two hemispheres. Whoops. And so there should be two edge modes, and that's why we have these two waves, the Kelvin wave and the Yanai wave. That's the manifestation of the bulk interface correspondence. Now, geophysicists worked out this wave problem in the 60s by considering a Coriolis parameter that varies linearly across the equator in a linear approximation. Matsuno, in particular, in 1966. They worked out this dispersion. So here are the gravity waves that are gapped, and then in the presence of some variation of the Coriolis parameter, then that 0 mode becomes dispersive, but at low frequencies. These are the planetary waves that we see also at the high latitudes. But so they saw these two other waves, these edge modes, but they realized that there was something mysterious about them. And when we sent our paper off to be reviewed, one of the reviewers said the question of why the equator supports a unidirectional wave, the Kelvin wave, was interesting scientifically and important mathematically. I've asked the question myself and have been unsatisfied with my answer, as well as the answer of other atmosphere and ocean scientists. So they knew there was something strange about these waves, but since they weren't exposed to these topological arguments, they didn't have that kind of way of thinking about the system. And this is really what we're seeing is an effect of the siloing of science. Atmospheric and oceanic scientists here probably don't go to your condensed matter seminars, and vice versa. And so there was a missed opportunity that could have been realized 20 years ago if they had been going to each other's seminars, and which I missed myself. So here's that angle resolved photo emission measurement, one of the topological insulators. And I want to now look at the atmosphere. And so this has been done by some atmospheric scientists. What they're doing is they're looking at satellite observations of cloudiness in the equatorial Pacific region and tracking the brightness of the clouds in space and time, and Fourier transforming those clouds. And these clouds trace a Kelvin wave traveling through the atmosphere, because when air is rising, it tends to condense into clouds. So the rising of the air is tracked by the cloudiness. And when they look at the power spectrum, the Kelvin wave emerges in the dispersion in the symmetric part of the spectrum, and the anti-symmetric part of the spectrum shows this dispersive Yanai wave. So this was done in 1999, before angle resolved photo emission spectroscopy had been done on a topological insulator by Colladis and Blue. So these waves are important in the climate system, as I mentioned. So the El Nino has widespread effects. It changes, in particular, rainfall patterns in North America. And if you come to my talk tomorrow, I'll say something briefly about our current cold period and what's going on. Yep.
RPET in spectroscopy, that's the momentum and frequency. How's it done over here?
So there's the waves are generated naturally, and but they have different wave numbers. So it's a superposition of a bunch of different wave numbers. So by taking a Fourier transform, by looking at a power spectrum in wave vector frequency space, then you get this that dispersion. So there's a whole bunch of waves, and just Fourier transform, yeah. That's right, yeah. You can actually see the effect of the El Nino on the concentration of carbon dioxide in the atmosphere. So this is a measurement in Hawaii of the carbon dioxide concentration. It's, of course, going up due to human input, and it's also oscillating on a yearly cycle due to the growth of plants in the spring, absorbing carbon dioxide and releasing in the fall. But then there's some additional structure that's visible in this black line where the seasonal cycle has been removed. And these bumps are largely due to the El Nino, because the El Nino has a number of effects on the carbon cycle in the atmosphere. And this was actually the first work that this is how I got involved with climate science, looking at these oscillations and noticing that there was a strong correlation between equatorial temperature, largely driven by the El Nino, and carbon dioxide going up into the atmosphere. So this isn't the greenhouse effect. This is occurring on a shorter time scale, but it represents a kind of positive feedback process where in warmer years, there are more fires, for example, in the tropical forests, releasing carbon dioxide up into the atmosphere. Now, there are many other oscillations in the Earth climate system, and this is, I think, the most remarkable one, at least for physicists. A lot of these oscillations are not oscillations in the sense that we think of in a physics class with high Q, for instance. They are pretty incoherent. The El Nino ENSO oscillation is varies between 2 and 5 years. It's very chaotic. This one up in the stratosphere is extremely periodic. It occurs every 22 months, and that's why it's called the quasi-biennial oscillation. What this is showing is the direction of the winds in the east-west direction up high in the stratosphere. So this is going from 20 kilometers to 60 kilometers in height, and the color change shows that a reversal in the direction of these winds very periodically. So quite remarkable. And it's believed that Kelvin waves in the stratosphere are part of the reason, or part of the driving force, or part of one of the mechanisms by which momentum is transferred into the east-west winds. So we decided to look at these observations of these Kelvin waves in the stratosphere and try to not just get the dispersion, as was done by Wheeler and Colodis, but to try to directly measure the winding number from the observations. So we went up to 20 kilometers in height and used something called reanalysis data. That's data that combines satellites and balloons and airplanes with models to interpolate between the measurement points. And we looked at we computed the winding number at low frequencies and high frequencies, and we found that indeed there is a vortex or an anti-vortex, depending on whether you're positive or negative frequency, in the high frequency regime. This is 1.5 cycles per day, so faster than the rotation rate of the Earth. When we go to low frequencies, then we just have this domain wall that's not topological, and that's characteristic of these low frequency waves, the planetary waves or the Rossby waves. So we're able to now use this as a tool to diagnose the character of the waves by looking directly at the winding number. Now, there's a nice story about some of this work that you can find in Quanta magazine from the summer of 2024, and talks more about Kelvin's discovery, and I recommend it to you. There are many other waves in the Earth system that are much more poorly understood, and this is one of them called the Madden-Julian oscillation. It's also occurs along the equator of the Earth, and it's a region of rain that slowly moves along the equator. And some climate scientists have suggested that a Kelvin wave may be implicated in these waves, but they're complicated because they're strongly coupled to clouds and convection. So we're asking the question, is there a topological character to this oscillation, or can we rule it out? So some of the tools that we've developed may be able to answer this question, and we're working on that now. So that's actually moving away from linear waves to nonlinearity, because convection can be very nonlinear. Here's another convecting problem. This is a model problem of rapidly rotating Rayleigh-Bernard convection, in which an edge mode is seen in numerical simulations. And some researchers recently have shown that they can compute the winding number, and they find a non-trivial winding number here that may give an explanation for this mode, which is topologically protected. If you put a barrier in this rotating cylinder, then the wave can go right around the barrier. Waves have been also looked at in active matter. Flocking, for instance, the wave equations are very similar to the shallow water equations and support these kinds of modes. There's been observations of Kelvin waves or presumed Kelvin waves in planets, Venus and Jupiter, and you can see some evidence for propagating waves here. We've been turning to plasmas. So the waves that I told you about on the equator were already identified by geophysicists, but we want to know, can these techniques be used to predict new waves? And so we've made such a prediction that in something called a cold magnetized plasma, there should be a wave at the edge of the plasma when it goes into a vacuum. And we've been looking experimentally for this wave at a machine at UCLA called the Large Plasma Device. And so the equations of motion are here. They're basically just Maxwell's equations plus the Lorentz force equation, and with some current, electron current, that's feeding back into the Maxwell equations from the velocity of the electrons. So if we linearize these equations, then we find that there is an edge mode that's propagating around in a helical motion around a cylinder of plasma. So this is a nice target for us to try to observe. And so this is the machine, and you can see the flash of plasma. These are probes that can be inserted into the machine. And what we're doing is we're sending in microwaves and then observing its propagation around the plasma. This gives you a kind of sense of the scale of this machine. So I'll show you some preliminary experimental evidence for these modes. We're going back in May for 2 weeks of more experiments to try to clean up, see if we can get a cleaner signature. But you can see that this is looking around the core of the plasma. So this is looking down the tube. There is some evidence for a chiral motion, but there's some complicated things occurring around the boundaries of the machine that we're trying to get a better sense of. So this would be this is a genuine prediction of a new wave. There have been other new waves predicted by plasma physicists using these topological tools, and we're busy trying to find evidence for them. These waves may be present in stars, that is, waves of topological origin. In the interiors of stars, for example, near something called the tachocline, which is the transition region between the radiative zone and the convective zone in the sun. So this field is just beginning, and we're building off the foundations that have been established by quantum physicists, but now extended to geophysical fluid dynamics and plasma physics. And so this now allows us to try to do some fundamental science, getting a better understanding of climate dynamics, maybe something called planetary superrotation, which I can tell you about if you're interested, solar plasmas, plasma physics. Possibly this will be useful for things like magnetically confined fusion or understanding climate change better. That remains to be seen, but now there's this kind of vigorous research program in place that we're pursuing. So what new waves of topological origin are waiting to be discovered? Thank you. I didn't mean to put that up, but I might as well put up an advertisement for the atheists.
Yeah.
Oh, cool. But like, maybe this is a bit of a technical question. Like, for both the Kelvin wave story and maybe later, like, how do I understand, like, to what extent would I hope to use linearized equation to capture the dynamics of a possibly nonlinear system? Like, I'm asking also because I guess this is a problem for quantum systems as well.
Right. Yeah, so that is a really interesting question, and something we are trying to come to grips with. So if we have systems with restoring forces, such as the Kelvin wave system, then at least theoretically, we can produce waves of arbitrarily low amplitude, and so we can be in the linear regime. And in the stratosphere, the waves that we were looking at, probably that's a pretty linear phenomena. But down in the troposphere, there's all the turbulence, the planetary boundary layer. It can be much more complicated. And so all of this, the mathematics, which we're carrying over from quantum physics, which is a linear theory, how to apply that in this nonlinear regime is a really important question. But I guess one hope that this might work is that, thinking about quantum many-body physics, which is also a linear theory when you think about the whole Hilbert space, it also often we think about it in terms of effective theories that are nonlinear, like a nonlinear Schrodinger equation, for instance. But that is a kind of model reduction from a linear theory. So perhaps these tools can be applied in this higher dimensional linear space. In the case of the fluid equations, we can think about a probabilistic interpretation in terms of, say, a Fokker-Planck equation. That Fokker-Planck equation lives in a much higher dimensional space, but it's linear. So that may be one route to trying to understand the nonlinearities or to trying to apply these topological tools, which are most at home in linear physics, by going up to this much higher dimensional space. So, but I think more, I invite people to think about this problem because I think it's very interesting. Yeah.
In the example diagram you showed with the two gravity waves above and below the flat band, outside of the equator, what factors can cause the origins of those waves to vary?
Because what?
Like the distance between those origins of the waves.
The gap?
Yeah.
So the gap depends on how far you are away from the equator, because it depends on the Coriolis parameter. So it goes to zero at the equator, and then it grows basically linearly as you go away from the equator, but then it's really, you're linearizing a cosine. So it's just that's determining what that gap is. Yeah.
So I guess two questions. So one is, I guess you mentioned that one of your issues that we're worried about is lack of a compact roll. So I missed it.
Yeah, I skipped over the technical details about that. So it turns out you can, in many situations, you can compactify the wave vector space. So in our original paper, you can show that you compactify it to a sphere, and the difference in the Chern number between the two hemispheres is an invariant. And there are other ways to compactify by like adding odd viscosity and so on. But I personally think that the winding number is a much maybe a more appropriate way to think about things, because so the Chern number is really inspired by the Kubo formula, so that gives it a nice connection to linear response theory. But here we don't have a Kubo formula, so why tie ourselves to Chern numbers?
The second question is, so it's interesting that you get this gap that we were talking about in the spectrum. But again, I guess condensed matter physics, we often try to argue for the existence of gapless waves by resorting to both of or some version of both of there, so they're probably not always correct. But here you seem to have opened the gap. So there are those, like, what is there a perspective of reconciling in Goldstone's term, or was it a Goldstone type of idea for why this gap is in the first place wrong?
Well,
so at f equals 0, you'd have had gapless waves. That would have been
yes. I haven't thought about it in those terms.
Sure.
But maybe we can talk about it. Yeah.
I was keeping an eye out for the thing you flashed on your first slide, which is broken discrete symmetries. I mean, one example that popped to me was this quasi-biannual oscillation at 22 months instead of 24. I don't know if I've missed any other explicit examples, but how can we think of this oscillation that breaks the time periodicity enforced by the
Time crystal.
yeah.
I see. Right. So that's interesting. Well, so I don't think there's anything really fundamental about that 22-month period. What the origin of those waves is due to gravity waves from disturbances in the troposphere propagating up into the stratosphere where the waves break. Because as the waves go up into this very low density air, then their amplitude grows. And then when they break, they can transfer momentum into the fluid. And so I think if you change some of the coupling, you would change the period away from 22 months. It's just the interesting thing about 22 months to me is that it's not commensurate with the seasonal cycle. It's just telling you the seasons aren't the driving force here. But recently there have been some hiccups in that oscillation where it like misses a cycle, which is kind of interesting, and it's led some people to wonder whether climate change is behind that or that's just a natural feature. So yeah, so there's some interesting questions.
So this is an interesting example of spontaneous breaking of time translation symmetry.
Yes.
Yeah. Okay. And like a crystal big step in time.
Yeah.
And those things you mentioned, like defects in crystal.
Yeah.
It's a defects in time crystal.
Yes.
So anyway, so yeah.
So you're using this Earth being a sphere to give you this, the rotating sphere to give you this Coriolis parameter. Have you looked for effects having to do with the curvature of the Earth more generally? For instance, if I think of quantum Hall in a curved space, I might expect that there are additional states that appear, which I might think would, in your context, would be additional modes of oscillation that you wouldn't expect in a flat space, time reversal broken system. And I was wondering if you could know what those even are in this context or look for them.
Right. So you could deform the Earth as long as there's an equator. So of course the Earth is actually an oblate spheroid, this it kind of gives you a robust explanation for these waves. So even if you had a very oblate planet, you would expect to have these waves. But if you change the topology of the planet, and sometimes we think about the so-called planet with two equators, because working on a sphere is kind of a pain in the neck. We often work on a doubly periodic system, a torus, but then we have to introduce two equators because the Coriolis parameter has to be periodic. So then there's two equators, and then it's kind of like the quantum Hall system. There's waves going in opposite directions on the two on the two equators. So I'm not sure if that is along the lines you're thinking of, but okay.
Yes.
My question, you might have answered somewhere in the talk, I might have missed it. but if we are trying to study the classical phenomena that happen on our current planet, and we are using rotating surfaces and trying to produce waves on it. Generally, in a physics-based model, you would need some sort of a driver to maintain the frequency of the wave, and then you can study the edge modes after you rotate the frame. But on the planet, what would that driver be?
So so the waves on planet Earth have lots of different drivers, but fundamentally the temperature difference between the equator and the poles is the most important one. So that sets up a kind of heat engine that is converting the high quality energy from the sun to infrared radiation, and some of that, a very small fraction of that, is being transformed into mechanical energy. So there are various instabilities of the fluid system that then start to generate these waves. And the El Nino, it's a complex coupling between the oceans and the atmosphere. And I didn't have time to go into all of this, but so there's a very interesting feedback of energy between the ocean and the atmospheres. There's some seasonal dependence to it. But fundamentally, it's all due to the energy input from the sun at the base.
And that maintain like a constant frequency, like our drivers would be good.
Well, the only thing that really had a constant frequency here of the waves was that quasi-biennial oscillation. The El Nino is really incoherent from a spectral point of view. It's spread out over a number of different frequencies. So it's really more of a chaotic system, and that's typical of most of the weather. Including the blocking that's occurring right now.
Okay, so fine.
Last thing, thank you for the very interesting talk. I was going to ask, how do you take into your analysis whether the groundhog sees his shadow or not?
That'll be the next theory. Right, a good place.
No more questions. I thank speaker again.
Thank you.